All right, so just want to make sure you're aware, you have your quiz 1 that you'll take online this week, going over basic chemistry this week. Probably finish up next week and start cells and tissues. All right. Let's see. All right, so let's start chapter 2. All right, again, matter is anything that has mass and takes up space. Matter exists as one of 3 states. It can be a solid, liquid, or a gas. If it's a solid, it has a definite shape and volume. All right, a remote, definite shape, definite volume. Okay, doesn't change. Liquid, okay, you might use a water bottle, soda. Okay, the liquid's just to the shape of the container, right? So you can move it, put it in a different container, it's gonna have a different shape, but it has the same volume, all right? Gaseous, or gas, you can change the shape and you can change the volume, okay? All right. So matter and energy. So matter may actually be changed. It can go through a physical change or a chemical change. If it's a physical change, you're not changing the basic nature of that substance. You're not changing the chemical composition. But if you change it chemically, you did change the chemical composition. All right? So if you boil water, what happens? It bubbles, it creates a gas, right? But if you cool that gas down enough, what would happen? It condensates back in the water, good. And if you froze, if you basically made that water super cold, then what happens? Freezes, becomes ice. But if you heat it up again, it becomes liquid water. The chemical composition is still H2O. Now, if you cook and you fry an egg, can you bring it back to its original state? No, why? Well, A, you cracked it, and B, if you cook that yolk, the chemical composition of that yolk is now changed, right? You can't bring it back, okay? Now, sometimes you can bring something back, but the point is it has a different chemical composition once you start cooking it, okay? All right. So related to matter is energy, and energy just means your ability to do work, okay? If you have energy, you can do stuff, right? If you have no energy, you can't do any work. So energy actually doesn't have mass, okay? It doesn't take up any space. And energy is said to be either kinetic or potential. It's potential if it's being stored, if it's inactive. But if it's being used, if it's doing work, it's kinetic. Okay, do y'all see the difference? If it's not being used, it's potential. If it's used, it is kinetic. It's kind of like you can have all the potential in the world, but if you're not doing anything with what you got, it's just potential, right? You got to do something with it. All right. Other forms of energy. So it can be chemical energy. It can be stored in chemical bonds, which we'll talk about later in this chapter. You have electrical energy, and that happens when charged particles move around. All right, mechanical energy. It's when matter is moving, it can create mechanical energy. And radiant energy, that travels in waves, like heat from the sun is radiation, right? Ultraviolet radiation, it's energy moving in waves. Okay, now how do you convert energy from one form to another? Well, ATP, which we'll learn about later, to adenosine triphosphate, it's going to trap chemical energy that's in your food. food that you eat, okay? And it traps that energy in bonds, in chemical bonds, right? So it can be used later. Okay, so you eat the food, you break it down, and you actually store some of that energy from the food in bonds. Okay. All right. So related to matter are elements. Anybody ever seen the periodic table of the elements before? Okay. All right. So it's not just a picture you saw in your chemistry class in high school. It's actual stuff, right? So these are fundamental units of matter. So believe it or not, 96% of your whole body is made up of just 4 elements. Okay. O, C, H, and N. Okay, however you want to remember that, CHON, or you want to remember it HONC, HONC. However you want to remember, it's 4 elements: oxygen, carbon, hydrogen, nitrogen. All right, those are your 4 most abundant elements in your body. And all the elements are on the periodic table. All right. So common elements making up the human body. You see that there, the oxygen, 65%. Yeah, oxygen, 65%. All right. Involved in organic and inorganic molecules. We'll learn about that in this chapter. Helps break down glucose, create ATP, energy. Carbon's about 18%. You see it in all organic molecules. See it in biomolecules like carbohydrates, lipids, proteins, and nucleic acids. Hydrogen's about 10%. You'll see it in most organic molecules. Okay, it influences pH, which we'll learn about a little later in the chapter. Nitrogen's about 3%. We see it a lot in proteins and nucleic acids, which are our genetic material. All right, calcium, phosphorus. All right. So calcium, you see it in your bones and your teeth. Also involved in muscle contraction, neural transmission of signals. Phosphorus, you see it in high energy compounds as well as nucleic acids and proteins. Potassium has a lot to do with muscle contraction and nerve impulses. Sulfur, important component of proteins. Okay. And particularly contractile proteins in your muscles, makes your muscles contract. Okay. All right, sodium, chlorine, magnesium, iodine, and iron, you see those a little less often. All right, but they are very important. Okay. All right, let's see. All right, atoms. Atoms are your building blocks, all right, of your elements. They're like our Legos, right? So atoms of elements will differ from one another. So an atom of nitrogen is going to be different from an atom of oxygen. Okay, and we'll talk about how they're different. So atomic symbols, these are chemical shorthand for each element. It just basically means abbreviations, okay? Indivisible, right? And we'll think about that, and we say that in the Pledge of Allegiance, right? So it means you can't divide it, right? So you don't divide atoms. Okay, subatomic particles, that just means parts of the atoms. So protons have a positive charge, P for positive. Neutrons have no charge, they're neutral. Electrons have negative charge. Okay. And Protons and neutrons live in the nucleus of an atom. Okay, electrons are not in the nucleus, they surround the nucleus. Okay. All right. So, what are the three subatomic particles again? Protons, neutrons, and electrons. Which ones are inside the nucleus? Which ones are outside? Which ones are positively charged? Which ones are negatively charged? Which ones are no charge? Okay. Neutrons, very good. So atoms going to be electrically neutral. So I thought you said neutrons are neutral. Well, they are. So we're talking about the whole atom, not just the subatomic particles. So here you got to look at how many protons you have. That's your positive charge. That has to equal how many electrons you have. That's your negative charge, right? Positive and negative have got to equal each other out or cancel each other out. Now, we also have ions. And ions are just atoms that lose or gain electrons. So then they have a charge, because then now they're no longer neutral, okay? The protons stay, but the electrons can come and go. All right. Now, we told you earlier, protons and neutrons are in the nucleus of the atom. They each have a mass of what we call 1 atomic mass unit, or AMU. And electrons, they're about 1/2000th of an atomic mass unit. Okay, so almost no mass. Okay. So I'll show you that. So yeah, 1 atomic mass unit for protons and neutrons, and almost no mass for electrons. Okay. All right. How do we describe or how do we show these particles? Well, one way we do that is through the planetary model. Anybody have to draw or do an old science project back in the day with the solar system and have your sun and all your rings around it with the different planets? Same kind of thing here. So here we're portraying the atom as a solar system, essentially. So the protons and neutrons are in the nucleus, or the center, like where the sun would be in the solar system, right? And then the electrons are in orbitals, kind of where the planets are in your solar system model. All right. So here's your example. Here's helium. So, all right, say hi, helium. Oh, he doesn't talk, sorry. So with helium, helium's got 2 protons and 2 neutrons in the nucleus, okay? It has 2, because it has 2 protons, it has 2 electrons outside the nucleus, okay? So here's essentially the center of your solar system, and then there's your ring for your planets, right? That's your planetary model. So we also have an orbital model, which is a more modern description of the atom, and it also helps to incorporate chemical behavior in the atom and how they behave. And the electrons are shown in what we call an electron cloud. So instead of just being in a ring, we put them in a cloud. And it's kind of a haze of negative charge that lives outside the nucleus. Okay. All right. So in this model, looking at helium again. All right. So, all right, say hi again, helium. Still won't talk. Okay. All right, so helium instead of having the lines, this is a planetary model. So this is planetary with the lines on it. This is the orbital model with the electron cloud. Y'all see the difference? Okay. Okay. All right, so electrons are going to determine atoms' chemical behavior. So remember I said earlier, I think I said this in your class, structure determines function. So structure, even at the atomic level, determines the behavior. All right, so this, even this, the planetary model is considered outdated. It helps us understand atoms and work with them. Okay. So this shows you atomic structure for 3 of our smallest atoms: hydrogen, helium, and lithium. Hydrogen has 1 proton in the nucleus. Helium's got 2 protons in the nucleus. Lithium's got 3 protons in the nucleus. Okay. What you'll see here is hydrogen and helium have 1 ring, 1 energy level, electron energy level. Only 2 electrons can fit in that level. And if you have more than that, you got to go to the next level. And that's why lithium has a 2nd level with 1 electron in it. Okay, and you can fit up to 8 electrons in that 2nd level. Okay. So based on the numbers, or based on what you've got written here, how many neutrons does helium have? 2, right? 2n0 here. It's 0 charge. How many neutrons does lithium have? 4 neutrons, right? The yellow ones. How many electrons does lithium have? Okay. How many electrons does hydrogen have? How many electrons does helium have? Okay. All right. Next concept is atomic number. So atomic number basically tells you how many protons are in that atom. Okay, it's a characteristic number for each element. Okay, every different element is going to have that same number of, or each, if it is carbon, any carbon atom is going to have the same number of protons in it. If you change the number of protons, it's no longer carbon. All right, and indirectly it tells you how many electrons it's going to have. Okay. Now the mass number has to do with the particles that have mass. What else has mass other than protons? Neutrons. So we got to add those 2 to get a mass number. Okay. Does that make sense? Huh? So you have atomic number, which is just protons. Okay, it's just proton. Mass number just means you're calculating how much mass there is. So then you got to figure out what has mass. Protons and neutrons have mass. So you got to add them together to get a mass number. That's all I'm saying. All right. So based on that, what's the mass number of hydrogen? 1. What's the atomic number of hydrogen? 1. What is the atomic number of deuterium? 1. What is the mass number of deuterium? What is the atomic number of tritium? What is the mass number of tritium? All right. Very good. So what you've just done is identify isotopes of hydrogen. All right. So there we go. So isotopes are atoms of the same element, which means they have the same atomic number, right? But they have different mass numbers. They vary in the number of neutrons. Okay, that's what you just did. Because remember, the atomic number didn't change, right? So that's what isotopes are. All right. So that's what we just did. Same number of protons, different number of neutrons. Okay, y'all see that again now? You see the yellow change, red stayed the same? Does that make sense? Okay. Okay, you need to understand isotopes to understand atomic weight. So it's going to be close to the mass number of whichever of those isotopes is the one that's most abundant. Which one you have most of the time. Okay? But the atomic weight reflects essentially the proportion of each. So like, I don't know, for those of you who remember looking at the periodic table, usually it'll have like the big number that or you'll have the atomic number that's big, and underneath it there'll be a little number that has a decimal, right? And it'll be like that number point dot 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 dot. So atomic number for hydrogen is 1, the mass number is 1.000 something, because there's a little bit of that deuterium and a little bit of that tritium out there. Not very much, but there's a little. So small impact on that atomic weight. Okay, that's all it's saying. I'm not going to ask you to do the calculation. I just wanted you to kind of generally understand atomic weight takes into context all of those isotopes. So if you see atomic weight on a question, it's probably going to incorporate isotopes. Okay? So even if you don't understand all the details of what an isotope is, usually you'll see those two terms together, right? All right. Okay, here's some examples. All right, calcium has a mass number of 40, atomic weight of 40.08. Okay. Carbon, mass number 12, atomic weight 12.011. Chlorine, mass number 35, atomic weight 35.453. Okay, so it gives you a sense of the relative proportions of some of the other isotopes. Okay, that's all it's saying. There we are. All right. So radioisotopes. All right. So radioisotopes just means you have an unstable isotope. Okay. And it decomposes. Okay, because it's unstable, it breaks apart. Okay. And it breaks apart to become the more stable version of the isotope, or more stable isotope. So what is radioactivity? Well, you know, you've heard things saying, well, it's radioactive, or you see the little sign that says radioactivity. All that means is some element can decay on its own. It's spontaneous. Right? It just breaks apart. And usually when things break apart, there's energy release, which in some cases can be really bad, right? Because it can cause things to happen. So that's what radioactivity is. So if you're working at the X-ray department, you might have, or CT, you might have some radioactive stuff down. And so you need to know how to deal with it, right? You need to know how to be careful. Okay. Molecules and compounds. So what's a molecule? Molecule means, go ahead and read it. Two or more atoms of the same elements combined chemically, right? That's exactly right. So same elements. Okay, that's the key word, same. Example here is chemical reaction forming a hydrogen molecule. Take two hydrogen atoms, connect them with a chemical bond, you get a hydrogen molecule, H2. Now, another important point about chemical reactions. You have reactants and products. Reactants are starting materials. Products are final materials, right? Reactants are on the left. Products are on the right. And the arrow usually faces to the right in the direction of the products. Does that make sense? So which one is the starting material? Reactant. Okay. All right. So what's a compound then? Well, I'm glad you asked. Well, a compound means two or more atoms of different elements, okay, that combine chemically and form some compound. All right, so here you take 4 hydrogens, 1 carbon, and you make methane, CH4, okay? So you're bonding the carbons and the hydrogens together. All right, and because they're different atoms, that's a compound. Does that make sense? So H2, we said, was a molecule because they're the same elements. H2O is a compound, okay? All right. Important thing to see here, these pictures, we're going to show you. Let's see. There we are. All right. So if you have compounds, they can actually have different properties from those of the atoms because you've combined them in a new way. So sodium is a very silvery metal, just sodium on its own. And chlorine is a very poisonous gas. You don't want to breathe chlorine, okay? But sodium chloride is just fine. You know, it's table salt, okay? Because you've created new properties by putting them together, okay? That's all that's saying. So that's a good way to describe what happens in a chemical reaction. You create some change. So chemical reactions happen when you combine atoms together or you dissociate atoms from each other. You take them some apart or put some together. Okay, it's a chemical reaction. Atoms, they get united by chemical bonds, right? We've been talking about that. Chemical bonds are the connection between the atoms. Atoms break apart or dissociate from other atoms when you break those chemical bonds, okay? Right, so we've talked about bonds. So in order to understand bonding, you need to understand electrons. Okay. So before we actually go on to electrons, I want you to talk to your battle buddy and explain the difference between molecules and compounds. So you can go ahead and do that now. You can do that at home if you're watching at home. All right, so again, we just left off a discussion about bonding. So let's talk about electrons and how they are involved in bonding. So electrons are going to occupy energy levels, and we call those electron shells or electron levels. And electrons more close to the nucleus are the most strongly attracted to the nucleus because they have the opposite charge, right? So if they're closer, you know, think about like magnets. when they're far apart, you don't feel them, but if you put them close together, you kind of feel that tug, right? When you put them together. Or if you just had a refrigerator magnet, when it's close, then you can kind of feel it tug on the refrigerator. So each shell or each energy level is going to have distinct properties. Number of electrons is going to have an upper limit, so it means you can only put so many in it. And you got to fill the shells that are closer first. Okay, so like if you're in a classroom, you got to fill the first row, second row, third row. You know, if I'm the nucleus, you have to fill and go back. All right. All right. So, all right. So bonding will only involve the interactions between the electrons in the outer shell. We call that a valence shell. Okay, so atoms with the full valence shells will not form bonds because they're already full. Okay, atoms bond with each other to get a full valence shell. So if they already have one, they don't need to bond. So if I want to, start a company, I'm going to partner with someone who's got strengths that I don't have. All right, we're going to get together, and then that way we can work together. Right? Or if I want to, create a team, I'm going to find people. If I play basketball and I'm a good shooter, I need to find some people who are good passers and good dribblers and good defenders, so that we can work together. Right? So that's kind of a basic primer on how shell or bonding works. I'll give you a little more information here. So if the outermost shell is complete, if the energy level is full, those atoms are stable. We call them inert. Okay, they don't interact. So how do we fill these shells? Well, we start at the bottom, right, like Drake, and we have 2 electrons that can fill the maximum or fill up that first level. All right, and then our second level can hold up to 8. Third level, and this is kind of a hybrid because technically you can hold a maximum of 18, but there's 10 of those that we're not really going to deal with. Okay, so you're mainly going to be using 8. Okay, so there's a section of electrons of that 10 or the 10 that kind of don't interact in the way that we're going to be teaching. Okay, so it's technically 18, but as we're going to do these, it's going to work out more like 2, 8, and 8. Okay. And I could get into that, but I don't think you probably want to, so I'm going to move on. All right, so here's an example of chemically inert elements, also known as noble gases. You may have heard that if you had chemistry in the past. Outermost energy level is complete. Okay, outermost energy level is complete. So for helium, the first level is full, 2 electrons. Neon, the second level is full with 8 electrons. Okay. All right. Okay, rule of 8s. That's what I was saying about the 2, 8, and 8. Atoms are considered stable when their outermost orbital has 8 electrons. Exception to this is shell 1, which holds 2 electrons. Okay. All right, reactive elements. So the outermost valence shell is going to be incomplete. So it wants to react with another element because it has an incomplete shell. So the atoms want to be like Tom Cruise and Jerry Maguire. They want to say, "You complete me," right? So the atoms are going to gain, lose, or share electrons to complete their outermost orbitals. The atoms are going to reach a stable state, okay, when they have a complete level. And they do that by forming chemical bonds. And then you get a stable valent shell. Okay. All right. So here are some chemically reactive elements because they have an incomplete valence shell, an incomplete outermost energy level. Hydrogen has 1 electron. Okay, how many total electrons can fit in the first energy level? 2. So it's, while it is neutral, it is chemically reactive, right? Carbon, how many electrons are in its energy level, the outermost energy level? How many are on the outermost energy level for carbon? 4, right? Count 1, 2, 3, 4. Also, it says 4e right here. How many total electrons can fit in the second level? 8. So is it complete? No. Oxygen, how many electrons are in the outermost energy level? 6. So is it complete? Sodium, how many electrons are in this outermost energy level? Is it complete? Now the question becomes, is it easier to give away electrons or take electrons? Okay, and it depends on how close they are to that number, right? So ionic bonds are one type of chemical bond. And they form when electrons are completely transferred, gained or lost, okay, from one atom to another. And it allows the atoms to achieve stability through transferring electrons, okay?
So for an example, like with oxygen and sodium, you wouldn't transfer that 1 to the 6 because it wouldn't complete it anyway, right?
You wouldn't unless you had 2 sodiums.
Right, then, so it can complete its
yes.
Okay.
All right, so this results from the loss or gain of electrons. So the term you need to know is anion. Anion happens when electrons are gained. And electrons have a negative charge, right? So anions are going to be negatively charged. Cations, another term you need to know, lose their electrons. And electrons have a negative charge, so if you lose positive, if you lose a negative charge, you lose your negative charge, you become more positive. So they have a positive charge. Another way to remember it, think of the T in cations. Think of it as a plus sign, okay, positive charge. And anions and cations are going to tend to stay near each other because opposites attract, right? The old Paula Abdul song, right? So, yes, I'm dating myself. I remember that, but that's okay. All right. So, all right. Hey, if it helps you remember, you can laugh, right? So, sodium and chlorine, right? We talked about these. Let's see. And, all right. So, make sure we're y'all on the same page I am. I don't think you are. All right, because I talked about ionic bonds gaining or sharing electrons. Okay, cations have a positive charge, anions have a negative charge. Okay. All right. So all right, so here's your picture, sodium ions. Sodium has 1 electron in its outermost energy level. It's going to be easier to gain 7 electrons or lose 1? Lose 1. Chlorine's got 7 electrons in its outermost energy level. Is it easier to gain 1 or lose 7? All right, so they find a mutually beneficial relationship here. So sodium gives up an electron, chlorine gains an electron. Now they both have complete outer energy levels. Everybody's happy. Make sense? Sodium, because it lost an electron, has a positive charge. It's a cation. Chlorine gained an electron, gained negative charge, so it has a negative charge. It's an anion. And this is an ionic bond. Okay, real quickly, we'll cover a little bit of covalent bonds. Ionic bonds deal with transferring electrons. Covalent bonds deal with sharing electrons. Okay. Covalent deals with sharing. Okay. Electrons are going to be shared in pairs. If you share 1 pair of electrons, you get a single covalent bond. You share 2 pairs, you get a double covalent bond. You will see occasionally 3 pairs shared, you get triple covalent bond. Okay. If for sharing of electrons involved, it's a covalent bond. All right. All right, you got your reacting atoms, hydrogen atoms, they're sharing. So they each end up now with 2 electrons in their outermost energy level. They get to double count them. Okay? That's 1 pair. So what kind of covalent bond is this? There's 1 pair shared. Single covalent bond. All right. Oxygen. Each has 6 outer electrons. They're each going to contribute 2 electrons. 2 pairs are being shared. Now they each have 8 electrons in their outermost energy levels because they get to double count those electrons. For each atom gets to count those 4 electrons. So 2 pairs are being shared. What kind of bond is that? Double covalent bond. All right. CH4, carbon and 4 hydrogens. Okay, carbon has 4 electrons, 4 hydrogen atoms contribute an electron, 4 single covalent bonds. Okay. And real quick, covalent bonds can be nonpolar or polar. If they're shared equally, the electrons are shared equally, it's nonpolar. Considered neutral. Okay. All right. So carbon dioxide, electrons are shared equally between carbon and oxygen. It's considered neutral, okay, nonpolar. But if the electrons are not shared equally, one atom is pulling harder than the other, it's a polar covalent bond, and you get positive and negative poles. And water does this. Okay, you get unequal sharing. All right, so water, oxygen has a harder pull on the electron, so you get negative pole for oxygen and positive poles for the hydrogens. All right. Hydrogen bonds are based on what we just saw with polar covalent bonds. These are weak chemical bonds, but they're not covalent bonds themselves. Hydrogen in one water molecule is attracted to the negative oxygen on another water molecule or another polar molecule. All right, and this contributes to surface tension, helps in intramolecular bonds. Okay, we'll see that next week. All right, so here are water atoms interacting with each other. Hydrogen slightly positive, water or oxygen slightly negative. All right, so they're slightly attracted to each other. That's hydrogen bonding. Okay. All right, and so this, and B on this side, this is surface tension. You have the water strider walking on the water. Okay, and you're getting these waters that are sort of attracted to each other and essentially allowing the animal to be on the water. Okay, and that's due to hydrogen bonding. All right, so we will stop there. Those of you who are going to lab, you can do your exit ticket on the way, and the rest of you, you can do your exit ticket now or do it at home. Yes.